Hi, in this video we are going to go through some worked examples using the determinant to solve problems involving matrices that have symbolic constants in them rather than just numbers. Let's begin with an assessment of singularity. If we're given a matrix that contains 4 different symbolic constants, A, B, C, and D, for what values of these symbolic constants is this matrix singular? I recommend that you pause your video, try to find the solution on your own, and then resume to follow along with my worked solution. The determinant itself is the key to solving this problem. We remember that there is an equivalence between the existence of a non-zero determinant and the existence of the inverse. There exists an inverse if and only if the determinant of A is not 0. So we want to look at under what conditions is this determinant equal to 0. We start off by evaluating the determinant. Doing elimination with symbolic constants often is a little bit of a pain, so we're going to take the expansion of cofactors approach to find this determinant. If you happened to have remembered the direct solution for a 3x3 using something like the rule of Saris, you're perfectly welcome to use that. I, however, will expand using cofactors. Expanding along the first row, we're going to end up with 3 terms that have coefficients of 1, negative A, and 1. And in each case, the matrix that we take the determinant of is found by crossing out the appropriate rows and columns. So this first matrix comes from crossing out the first row and the first column. The second matrix comes from crossing out the second row, or second column, and the first row, left with B1, C1. And the third determinant is found after we delete the first row and the third column, B1, 1D. Then we simply evaluate these directly. 1 times 1 minus CD minus A times B minus C plus BD minus 1. Right? This is an expression for the determinant, but it's not in a form that lets us really do anything with or to determine what relationship between the symbolic constants would give us a singular matrix. So we need to do some simplification. We first of all expand out all of the terms from the various parentheses, 1 minus CD minus A times B, minus A times negative C plus AC plus B times D minus 1. And we notice that the 1 and the minus 1 disappear. We now want to see if we can simplify this. Learning how to sort of identify which pieces to group together and factor out is something that comes with practice. So if this was a little bit tricky to you, don't worry overly much, but it is good to try to develop this practice. We can group these terms. If I look at these, I recognize that there are 2 terms that contain an A in them. These terms both contain an A. And the other piece is a C and a B of opposing signs, a negative AB and a negative AC. And there's another grouping that we can make that has 2 terms with a D. The D, again, both with a B and a C as the other component, and of opposing signs. So let's factor the a out of the first term, giving us a times c minus b, and factor the d out of the second pair of terms, giving us d times b minus c. B minus c is just negative of c minus b, so I could replace this with a negative and change the order of those terms. And then I have c minus b and c minus b. We can factor that term out, and we're left with a product a minus d times c minus b. When we're trying to assess singularity, it's always nice to be able to express something as a factor of terms, a product of terms, because we're interested in the case where a equals 0. Sorry, the determinant of a is 0. If we can express the determinant as a product, then the determinant will be 0 if any one of those individual terms is 0. So the determinant of a will be 0 if either a minus d equals 0, which means a equals d, or if, and this should be a b here, or if c minus b equals 0, giving us b equals c. If we think back against what this matrix is, that makes sense. If a equals d, then we will have a row 1a1 and a row 1a1 for the first and third rows. Identical rows give us singularity. If b equals c, 1b1, 1b1 gives us singularity. We could have come up with these conditions without computing the determinant, but we wouldn't have been sure that there weren't any other constraints. What this approach lets us know is not only are these the cases that give us that these cases do give us a singular matrix, it also tells us that there are no other cases that give us a singular matrix. Okay, let's go on to another example using Cramer's rule. And I'm going to provide you what Cramer's rule is as a reminder here. Cramer's rule allows us to get a solution to a system of equations as ratios of determinants of these constructed matrices B, where we replace a column of A with the right-hand side. The system we're considering is this one here. x1 equals ax2 plus ax3 plus b, x2 equals ax1 plus ax3 plus b, and so on. This may remind you of the Leontief equilibrium, economic equilibrium kind of structure. That is the sort of structure we have here, a set of overall demands on one side that are described by a set of internal demands plus a set of consumer demands. But this problem is structured in such a way that the diagonal terms, that is the demands from within a sector, are created as 0. This can be thought of as an economic problem where we are only looking at the so-called marginal output, that we factor in the sort of internal requirements, internal uses within a sector of an economy, and subtract those out before we consider what the output is. Right? When we do this, so can we find a direct solution to this type of economic equilibrium problem with an additional constraint of symmetry, that all of the external demand coefficients are, sorry, all of the other internal demand coefficients are the same, and the consumer demands are the same. I recommend that you pause your video at this point, try to solve this problem on your own, and then resume to follow along with my solution. The first step in this has to be recasting this in matrix form and in the appropriate matrix form. We have looked at this class of problem repeatedly, and so the general formulation that we're going to want to take for this type of a problem is to actually break it into 3 pieces: a vector of x's on our left-hand side, a block that can be expressed as a times x, and a additional vector of b. And we can rearrange this into a form of I minus ax equals b, which allows us to cast the problem in the standard form of m times x equals b. We need to have a system in this form for any of our solution approaches to work. We need to do this in order to use Gaussian elimination or LU decomposition. We need to have our system in this form to use the matrix inverse. We need to have our system in this form to use Cramer's rule. In this context, A is the coefficient of the matrix of coefficients shown in the first block. So this gives us 0AA, A0A, AA0 for our matrix A. M, of course, or B, of course, is just the matrix of all B's. And our matrix for mx equals b is given by I minus A. Since we had zeros on the diagonal, this difference gives us ones on the diagonal and negative a's on all of the off-diagonal pieces. Now that we've set up things in matrix form, we're ready to address the problem with Cramer's rule. I've included Cramer's rule at the top here as a reminder that each of our individual x values will be solved by a ratio of determinants, where the numerator is the determinant of a matrix where we replace the ith column of the target matrix with b, and the denominator is always the determinant of our original matrix. And our original matrices here are the M matrix, 1 minus A, and our right-hand side, B. First step is to compute all of the determinants that we need. Starting with M, we can once again use a cofactor expansion to do this. Expand along the first row. The 1, 1 term will be positive. The 1, 2 term will be negative, and the 1, 3 term will be positive. So positive 1 multiplied by the matrix that we get when we delete the first and the row and column here. Then for the second term, negative of negative A, positive A, multiplied by the determinant when we delete the second column in the first row, the determinant shown here. And thirdly, we have the positive sign, so plus negative A for our coefficient, and the determinant of the matrix when we delete the first row and the third column, shown here. Once we've done this, we can just go through and evaluate these 2 by 2 determinants. 1 times 1 minus negative a squared, or 1 minus a squared, plus a times negative a minus negative a squared, and minus a times negative a squared, which is a squared, minus negative a plus a. That gives us our expression here. Again, it's always a good idea to try to simplify these expressions. We begin by multiplying out everything to give us 1 minus a squared minus a squared minus a cubed minus a cubed minus a. And then to group like terms, we have a negative a squared, a negative a squared, and a negative a squared to become negative 3a squared, a negative a cubed, and a negative a cubed to give us negative 2a cubed. It's fine if you want to leave it at this point. We will learn more, and we will find a much more simpler, more interesting solution if we're able to factor this. How you factor polynomials, again, there's a bit of intuition involved. You might look at this and say, when could this be equal to 0? One way to know when this would be equal to 0 would be to say, let's say, try a equals 1. If a equals 1, we'd have 1 minus 3 minus 2. Well, that's not 0. But what if a is minus 1? If a is minus 1, we'd have 1 minus 3 plus 2, which is 0. That suggests that a equals minus 1 is a solution to this being equal to 0. We rearrange this to give us a plus 1 equals 0, and this is a factor of this expression. If we factor out this a minus 1, what we actually end up left with is, so a plus 1 multiplied by, what we're left with is 1 minus a minus 2a squared. And this also has a pair of factors, 1 plus a and 1 minus 2a. And this gives us a overall factorization of this shown here. Again, this is not something I am really expecting you to do right now. I'm showing you the process of how we can think about this. This is our determinant m. We now go through and apply exactly the same process to our 3 b determinants. b1 is found by replacing the first column with b's. That gives us our matrix here. We evaluate the determinant in the same way, expanding along the first row. B times the determinant we're left when we delete these two, plus A times the determinant that we are left with, plus A times the determinant we're left with when we delete those two, minus A multiplied by the determinant we're left with when we delete the first row and the third column, as shown here. Same approach, B times 1 minus A squared, plus A times B minus negative AB, or plus AB, minus A times negative AB minus B. What we have here. Multiply everything out, B minus BA squared plus AB plus A squared B minus a times negative ab is plus ab squared. Minus a times negative b is plus ab. Once again, group-like terms. Plus ab and plus ab gives us 2ab. Negative a squared b plus a squared b, these cancel out, leaving us with a single a squared b term. We see that all of these terms have a b, so we factor that b out. That leaves us as 1 plus 2a plus a squared. This is simply 1 plus a squared. And so we have a simple form for our B1. For our B2, we do exactly the same thing, except that it's the second row that we replace with B's. Calculate the determinant in exactly the same way. Begin with an expansion. I'm going to choose the first row, 1 times the determinant that we're left with when we delete the first and the second row. That is the determinant of this block. Minus b, moving to the second piece, times the determinant that we get by deleting the first row and deleting the second row, the second column. Negative a, negative a, negative a, and 1. Minus a times the determinant that we get when we delete the first row and the third column, shown here. Evaluate these determinants. 1 times b plus ab minus b times negative a minus a squared minus a times negative ab minus ab. This term is equal to 0, so we can ignore that whole piece. B plus ab minus gives us a plus ab minus gives us a plus a squared b. Group-like terms gives us again the same answer, b minus 2ab plus a squared b, which we've seen how we can factor into this form. And then go through to B3 and do the same thing. We replace the third column with B's and go forward with evaluating the determinant. With our expansion along the first row, 1 times the determinant that we get deleting these 2 rows, which is this matrix here, plus a, moving over and changing the sign, multiplied by the determinant of negative a, bb, plus b, giving it multiplied by the determinant of the matrix negative a, 1a. Again, evaluate the determinants. B plus ab plus a times negative ab plus ab plus b times a squared plus a. Once again, we have a term that goes to 0, so we can ignore that piece. A plus ab plus a squared b plus ab, group-like terms, ab and ab gives us 2ab. We have the same result once again, which we know how we factor. Summarizing all of our results, we have a general result for the determinant of a, and we've actually found that the determinant of B1, B2, and B3 are all in fact the same. This is not surprising given the symmetry of the problem. we're asked, this looks like an economic problem where every sector behaves in exactly the same way with respect to the other sectors and has exactly the same set of consumer demands. It makes sense that the solution would give the same answer for the outputs of all of the sectors. All right. Okay. So how does this finally all go together? Our solutions are each given by a ratio of the appropriate determinant over the determinant of the original matrix. And sorry, this should not say A here. We should have this xi equals bi over m. And remember that our m has negatives in all of these pieces. Sorry about that. Slight mix up there. The determinant of m is this value. And we compute then this ratio. For all of our b's, we have a numerator of b times 1 plus a squared. And for our determinant m, we have 1 plus a squared over 1 minus 2a. Before doing anything else, we should recognize what the constraints on a are. A cannot be -1 because that would make us have zeros, and a cannot equal half. If we think about the meaning of our original system, well, a equals -1 would be a kind of ridiculous answer anyway. It would require negative requirements from one sector to produce another. Right? That doesn't make sense within the real world problem. But we can see why this would give us a problem mathematically. If a is -1, this matrix is a matrix of all ones and obviously doesn't have a solution. However, we also have a constraint where a cannot be equal to half. What does this mean? This is a context in which you need half as much of the output value from each of two other sectors in order to produce that amount of output from one. This is a case where we don't have a profitable answer or profitable economy. Each sector of the economy needs to use all of its output to produce results from the other side of the other portion of the economy. That cannot give an answer for a non-zero b. Right? So we have a second failure point. As long as a is not one of these values, then then this will give us a well-defined answer. We can simplify this by canceling out the like terms here, and that gives us quite a simple result. The general solution to this system is b divided by 1 minus 2a. If you think about what this is, b is the consumer demand, and the amount that we need to produce is linear in the consumer demand. And the denominator is 1 minus 2a, 1 minus the sum of how much we needed of input from the other sectors of the economy in order to produce a certain amount of output. The larger a is, the smaller the denominator is, and the larger the total amount that we need to produce is. So it all makes sense within the context of our problem. Let's go through one last example problem, finding an inverse of a matrix that has a lot of symbolic constants, using the classical adjoint approach. The classical adjoint approach allows us to directly compute the inverse of a matrix as the inverse of the determinant multiplied by the so-called classical adjoint, which is a matrix made up of the cofactors. So let's try to use this to find the general inverse of this matrix that has symbolic constants A and B, but also has a lot of structure to it. I recommend that you pause your video, try to work through the solution, and then carry on to watch my worked solution. Okay. So we have our given matrix and our formula for computing the inverse with the classical adjoint approach. One of the pieces we need for this is the determinant of A, so let's start there. Once again, I'm going to use the cofactor expansion approach to do this. Expanding along the first row, A times the matrix that's left over after we ignore the first column and row, which is 0BBB as shown here, minus A, moving over to the next column, the matrix that we get if we delete the first row and the second column, A0 and BB, and the third term, which has a coefficient of 0. So in fact, we don't even bother really needing to think about what this determinant is because we know that we have a coefficient of 0 here. Evaluating these determinants, A, 0 minus B squared minus A times AB minus 0, we see that even just having a few zeros along the diagonal simplifies the calculation of the determinants a fair bit because we have terms that simply disappear. This is negative AB squared minus A squared B plus 0. Both of these terms have a common AB, so I will factor that out, and I'll also factor out the negative to give negative AB times A plus B. This is our determinant. The way that the determinant of A is used in the classical adjoint is by taking the inverse of it, which means that this matrix can only have an inverse when a determinant of A is non-zero, which is our standard result. The determinant of A not being equal to 0 means that A can't be 0, B can't be 0, and A can't equals negative B. If A was equal to 0, we would have a 0 row. If B was equal to 0, we would have a 0 row. What is less obvious is that if the matrix had the form A0, A0, negative A, and 0, negative A, negative A, this is a singular matrix. Okay. Let's now move forward to evaluating our matrix of cofactors. So each of these involves a determinant, but it involves a small determinant. Right? Remember that the cofactors have a sign term determined by the sum of the values I and j, and a determinant term, which is the determinant of the matrix that we get by crossing out the appropriate row and column. So C11, we have a positive term because 1 plus 1 is 2. And the matrix we find the determinant of, we get by crossing out the first row and the first column, shown here. This, of course, is 0 minus b squared, negative b squared. The C12, 1 plus 2 is 3, so we have a negative term. The determinant is found by deleting row 1 and row 2, and column 2. A0, BB is AB minus 0 with our negative term, negative AB. Our 1, 3 cofactor, 1 plus 3 is 4, so we have a positive term. They delete row 1 and column 3. It's the matrix A0, 0B. AB minus 0, so positive AB. And we do exactly the same thing for our next row, and then again for the third row. 2 plus 1 is 3, so we have a negative. Delete the second row in the first column, leaves us with AB, 0B. The determinant is A times B minus 0 with the negative here. For 2, 2, same thing. 2 plus 2 is 4, plus, delete the second row and the second column, leaves us A0, 0B. The determinant is A times B minus 0 for a result of AB. For the last term from the third row, 2 plus 3 is 5. So we have a negative number. We delete the third column and the second row, leaving us with AA0B, A times B minus 0 with the negative, negative AB. Carrying along for the last row. 3, 1. 3 plus 1 is 4, so this is a positive term. We delete the first column and the last row, gives us the matrix AB, A0, 0B. Determinant is A times B minus 0, so we have AB. For the 3, 2 cofactor, 3 plus 2 is 5, so again we have a negative number. Delete the third row and the second column, leave us A0, AB, A times B minus 0. With the negative, gives us negative AB. And our last cofactor gives us 3, 3 is plus 6. 3 plus 3 is 6, so a positive number. We delete the third row and the third column. We're left with the matrix A0, 0 minus A squared with the positive multiplication gives us negative A squared. This is a lot of work. Using the classical adjoint to find an inverse is a lot of work, but working through Gauss-Jordan elimination with symbolic constants is also a lot of work. Right? This is a fair bit of work, but it's hard to make mistakes in this as long as we're careful. The arithmetic is all very straightforward. Right? Okay, moving forward, I've summarized the set of cofactors that we just calculated. I've summarized our determinant that we've calculated. These cofactors can be placed into a matrix. See? The matrix that we want to use for the inverse is the transpose of this matrix. Very important to remember that we actually want to take C transpose. However, in the example that we were working with, we note that actually the original matrix was symmetric. A transpose equals A. And the result is also, the cofactor matrix is also symmetric. Right? And thus, the C transpose just equals the same as this matrix here. Right? The final result for the inverse is this transpose of the cofactor matrix, which is the same in this case, multiplied by 1 over the determinant. as we've shown here. We have a general expression for the inverse. It is perfectly fine at this point to leave it in this form. However, you might notice that we have a lot of similar terms here, ABs, and we have an AB here. If you want to simplify this, we actually find that we can. We can essentially take this 1 over negative AB and multiply all of the terms in this matrix by negative 1 over negative AB. All of the negative ABs then just become 1s. All of the positive ABs become negative 1s. And the term here, negative B squared over negative AB, the B cancels out here and we're left with B over A. Similarly, negative A squared over AB, so negative AB, the A cancels, the negatives cancel, and we're left with A over B. So B over A in the upper left corner, so B over A in the upper left corner, A over B in the lower right corner, negative 1s on the diagonal and 1s in the other places, and then a simple scaling factor of 1 over A plus B. Once again, we remember that A and B can't be equal to 0, and A can't equal negative B. With this general form, these restrictions make sense. A can't be 0 because that would mess up this term. B can't be 0 because that would mess up this term. A can't equal negative B because that would mess up this term. We have a final result with all of our restrictions on A and B. That ends our worked examples using the determinant and wraps up the videos for this unit on the determinant. You'll have more opportunity to practice these ideas on the homework. Thank you and goodbye.